Okay, this lesson is on what's called linearization, and you may or may not have heard this term before, or maybe you don't recognize it, but it is actually something very similar to what you've been used to. Now I want you first to think about a function, and here I'm going to have us think about y equals to x squared. So a very nice simple quadratic equation. So if we had y equals to x squared, you guys know that it looks something like this. And what does the graph look like when you zoom in really, really close to it? Because you know that you have a parabola, and it is not made up of straight lines. But if you zoomed in really close to it, let's say at the point 1, 1, this is not to scale, but let's just say that this is the point 1, 1, what would this little piece of the graph right here look like? I'm going to pull up the graph of y equals to x squared. And I want us to take a look at it. So what we're going to do is zoom in at that point where I have my cursor at about 1.5 and take a look at the graph. What is happening to our parabola? We'll zoom in one more time. Can you tell? What does it look like? What does it look like is happening to our graph? And one last time. So now if you take a look here, this now almost looks like a straight line. You can look at it over here on the left hand side or over here a little bit bigger. When you zoom in really, really close, things just start to look like lines. Now, no matter how curvy or how non-linear it is to begin with, if you zoom in close enough, it is going to look like a straight line. And that concept that we're talking about is called linearization. And when we zoom in close enough, that straight line is actually our tangent line at that particular point, or at whatever particular point you are concerned with. So, having a little trouble here drawing this line. Oops. Okay, so there's my really crooked tangent line. So we're going to do an example. Given the function f of x equals to x squared, I want us to show that the tangent line at the point 1, 1 is y equals to 2x minus 1. Okay, so how do we approach this? Well, the first thing you got to do is take your function and find out its x and y value at that point. So of course it's f of 1 equals 1. And we need to find the slope. So that means f prime of x, which is 2x. So f prime of 1 is going to be 2. So the slope at this point right here is going to be 2. The slope of the tangent line. So now how do we actually write out the equation that we need? Well, y minus y1 equals to m times x minus x1. So we have y minus 1, our slope is 2, and x minus 1, because we're using our point 1, 1 with our slope of 2 to write the equation of the tangent line. So y equals to 2x minus 2 plus 1, or y equals to 2x minus 1. So now this should be something you're already used to. Hopefully you guys remember how to find equations of tangent lines from your previous class. And now I want to generalize this and write out what we have for linearization. Okay? So if we have some function f that is differentiable at some particular point, x equals to a, then we say that the approximate function, which is L of x, equals to f of a plus f prime of a times x minus a, is what we call the linearization of f at a. Now keep in mind, all this is the equation of the tangent line. That is all this is. And now why couldn't we have just said that? Because you need to understand that when you zoom in super close, it will look like what the tangent line is. Okay? Now we call this point that we use here, x equals to a, the center of the approximation. Because basically, that equation of the tangent line, or the linearization, really only works around the point 1, 1, because if you move away to another point, for instance, say 2, 4, it has a different slope at that particular point. So I'm going to do one last thing with this and show you how it ties in. You know how y minus y1 equals to m times x minus x1. That's our point slope form, right? So if I were to rewrite this by solving for y, this is what I would have. And what is y sub 1? That is your f of a. And what is your slope? F prime of a. And then we have the x minus a still, where your point is a comma f of a. Instead of x and y, it's a f of a. So you guys notice where all of these things fit in onto here. So this is the form for the linearization. Hopefully you can see the similarity. All right. So what we're going to do now is find a linearization for f of x equals to x cubed minus 2x plus 3 at x equals to 2. So how do we start this off? We need to find f prime of x, and since f of x is given, to take the derivative, we have 3x squared minus 2. So that means we need to find out what f of 2 is. We need the slope at that particular point. So that means 3 times 2 squared minus 2. So we have 10. We also need to know our point, so that means f of 2, and that's 8 minus 4 plus 3. So we have 7. So plugging everything into our linearization equation, which is L of x equals to f of 2 plus f prime of 2 times x minus 2. We have 7 plus 10, this is an f prime over here, plus 10 times x minus 2. So 7 plus 10x minus 20 gives us 10x minus 13. And that is our linearization, meaning what the equation turns into when you zoom in really, really, really close into it. Now let's try another one. I want us to find the linearization of f of x equals to 1 plus x to the k power. Oops, that's kind of hard to see. Let me rewrite that. 1 plus x to the k power. And this is going to be for all k at x equals to 0. Now this is a new symbol for most of you guys, I think. This is a mathematical symbol, notation that we use. It means for every. So it's just sort of a shortcut. Like you guys typically know this one. That means therefore with the 3 little dots. Well, this one means for every. Okay, you'll see me use it again. Alright, so we have f of x, and we can go ahead and find f of 0. So that's going to be 1 to the k power, which is 1. And we need to find the derivative, so f prime of k. Remember, k is going to be some constant, so we can do the power rule here. That is not our variable. So I have k times 1 plus x to the k minus 1 power. Now, what does the derivative equal to at 0? Remember, k is a variable, or k is a constant. So it'll be k times 1 plus 0 to the k minus 1 power, which is still going to be a k. So writing out our linearization, L of x, it's going to equal f of 0 plus f prime of 0 times x minus 0. So f of 0 is 1, f prime of 0 is k, times x. So that means if we have an equation or a function of the form 1 plus x to the k power, its linearization is going to be 1 plus kx. So let's do one last example based on this. So using the results from example 2, I want us to find the linearization of f of x equals 1 plus x to the 2/3 power for every k at x equals to 0. And so this last part here must be set up the same. We need to be centered about the same thing, which in this case is 0. Okay, so since we have this generalization up here above, all I need to do is plug in what k is. Well, what's k? K is 2/3. So therefore, L of x equals to 1 plus 2/3 x. And it's as simple as that. And I can vary it up a little bit and change the form of the equation, 1 plus x, inside in the parentheses, and that's what we can work on tomorrow for our assignment. I'll go over more of that with you guys. If you want to view another video with some other examples for related rates, I'm going to put that up as a separate one, since you will have 2 more problems involving, oh, I'm sorry, not related rates. We will have 2 more problems involving optimization for tomorrow's assignment.